many weeks ago, this Climate Change 101 seminar series. And the idea originated the year before at a retreat up at the Tahoe Research Center to see how the University of California can bring our intellectual resources to the state and the community, help you better understand climate change. So today is the finale, I guess the 12th in this series of seminars. And the goal here really is to allow you an opportunity to follow up on questions you might have had from previous seminars and to just have a question and answer with the panel. And I'll introduce the panel very quickly here. Brian Weir, who spoke earlier in the series, UC Davis, Phil Duffy, also, who you should know, organizing this. Ian Falloon is new to our panel, so maybe you could just tell us a real brief statement about yourself and what you do in terms of climate change science.
All right, I'm an atmospheric chemist who works on biogeochemistry, how the biosphere influences the atmosphere and the climate.
Great. And Jeff Mound, who you've seen before in one of the earlier presentations. So again, today's goal is to really have you ask lots of questions, and hopefully we can answer most of them. So I think we'll start there. When you ask a question, please speak loudly enough. The microphone should be able to pick that up. Loudly enough so we can hear the front. People outside can also be. So with that, let's begin with some questions. I don't think it's necessary to come up to the mic. We'll be able to pick up from the back. So questions. Who wants to be first?
What would you say to the global warming skeptics that say that rather than carbon dioxide molecules in the atmosphere causing that it's some sort of solar radiation warming the oceans that's causing water vapor to evaporate, and that's really where a lot of the carbon dioxide is coming from?
Well, there are, I guess, two parts to that. One is in terms of solar variability and the radiation aspect of it. The other part, they believe to others on the panel dealing with the evaporation and feedback mechanism. But with regard to the sun does vary over many time scales. The most pronounced one is the 11-year solar cycle, which many of you might be aware of. And those variations impact the atmosphere, but in a very small way compared to what's happening with greenhouse gases. So in terms of solar variability, it's part of the climate change mechanism, but not the primary part now, and it's going to get smaller relative to the increases in greenhouse gases in the future. Now, in terms of the feedback, maybe, Phil, do you want to follow up on that?
But to add one more thing about solar variability, what we know, if there's speculation about solar variability, by which I mean changes in the energy output of the sun going back centuries, but what we know with certainty about solar variability is from satellite measurements made over roughly 25 years. And what we see in the satellite measurements is changes in solar output that are very small, like 0.1%, and also cyclical, so they go up and down with an 11-year cycle. So, that can't possibly be responsible for a steady increasing trend in global temperature over 25 or 50 years, which is what we've seen, because it's cyclical. As far as the question of, your question mentioned what we call a water vapor feedback, and you also mentioned the issue of carbon coming out of the oceans. And, first of all, I'm sure you've seen, the increases in atmospheric carbon dioxide are measured and repeatedly, and they're real. No question about that. And in fact, if you compare the increases in the carbon content of the atmosphere to the emissions, and we have a pretty good idea, we think, of what the emissions are from burning coal and oil, natural gas, and so on. If you compare what we've added to the atmosphere to what is observed to be accumulating there, actually what's accumulating in the atmosphere is much less, not much more. So there's really no need to invoke a mysterious source of carbon to explain the observed increase in atmospheric CO2. And in fact, what's happening is, and the reason that the emissions of carbon into the atmosphere exceed what's accumulating there is, as the statement applies, a lot of the carbon that we add to the atmosphere is disappearing somewhere, and a lot of it, in fact, is going into the ocean. So the ocean at the moment is a sink of carbon. not a source. And the rest of it is the other major sink is the terrestrial biosphere, plants and soils. Those things are acting as, on the whole, as sinks, which is a good thing. You want to add to that?
I would just say that the you mentioned warming of the ocean, and that, of course, is part of global warming. So any energy you put into the ocean is going to have profound impacts on the climate. So there's a little bit of a disconnect there in terms of being skeptical. If the sun is heating the ocean, that's part of the issue. Definitely.
Do you want us to give our name? Can we ask her? Okay, Art Collins, ARB. Let me have a follow-up to that question. I'm aware that the standard IPCC position is that the variability in the solar output is insignificant from the standpoint of global warming. However, let me point out that if you look at the carbon-14 in tree rings and in various geological material, this is a proxy for solar output, because the carbon-14 is generated in the atmosphere by cosmic ray bombardment of nitrogen-14. Okay, in essence, you get a spallation neutron from cosmic ray, impacts the nitrogen-14. The nitrogen-14 absorbs the neutron, emits a proton, and becomes carbon-14 with a half-life of 5,300 years. But the point is, therefore, the carbon-14 is a proxy for cosmic ray intensity, which in turn is a proxy for solar output because of the variation of the magnetic field. The solar wind varies with the sunspot cycle. It pushes out the magnetic field, which reduces the cosmic ray flux. So in any case, what you see is a very good correlation between temperature, and there the proxy is the oxygen 18, oxygen 16 ratio, and the carbon-14 ratio, which is the proxy for solar radiation, and they correlate very nicely. You have the Maunder minimum, which was 300 years ago. You have the Sporer minimum, 500 years ago. You have the Wolf minimum, 600 years ago. You have the medieval maximum warming, 800 to 900 years ago. And you have the Oort minimum, 950 years ago. Now, those are carbon-14, and they correlate with temperature very nicely. So that kind of historical data suggests that the solar variation is a significant factor, and yet the Intergovernmental Panel contends that the solar variation is an insignificant factor. Incidentally, according to carbon-14 data, right now we're at a stage of very high solar output compared to all this historical data extending back over 1,000 years. So that my question.
I mean, everything you're saying about, well, I'm sure Terry will want to comment, but I think you may be misunderstanding what the IPCC is saying. The IPCC is not saying that solar variations are insignificant on the timescales that you mentioned. You mentioned eras in the Middle Ages and so on. The IPCC is making a statement that on the timescale of the last 50 years, that solar variations are insignificant. And even, in fact, as recently as the early 20th century, it's thought that solar variations are actually significant, and the observations show a very rapid warming during the 1920s, which is not explainable by greenhouse gases.
Right.
I mean, there simply wasn't a rapid greenhouse gas buildup in the 1920s, and it's thought that that's largely a result of solar variability. So I don't think there's a real inconsistency.
Okay, and I should mention one more thing about the solar irradiance issue. When people refer to the 0.1% variation being very small, that's in total solar irradiance. There's much greater variations in the UV part of the spectrum, which affects ozone, which can provide linkages to other parts of the atmosphere, and that's being looked at now. So to follow up on Phil said, it's significant, but relative to what's happening recently, it's not as important or as significant as what's happening with the greenhouse gases. But the sun is playing a role, but compared to what's going on now, not as important.
Ellen Self, City of Sacramento. I have seen projections and literature about what could happen in the next 100 years, but I haven't really seen very much beyond the next 100 years. What has anybody looked at 200, 500, 1,000? Are we in any danger of turning Earth into Venus or anything like that?
And there's a feedback there that will probably keep us from turning into Venus. Well, one of the things that I think Phil can probably comment on better than I can is that you're right. We tend to have this benchmark, which has been the magic 2100, and we can't think beyond it yet. There's a lot of work just in the last year or so where people are saying what we're seeing is a lot of phenomena have a very long lag time. And then, in fact, things like sea level rise, which we're now getting all agitated about, and there's just an issue, and it came out, it was in Nature, I guess, that just said we hadn't measured it correctly. In fact, it's rising faster than we thought. Where we really are going to see the major effects of sea level rise in the next century rather than in this century. So people who are starting to focus on that are recognizing that in the next century there will be some substantial changes. And of course, you got to remember the residence time of CO2 is quite long. So what we do today sticks around for a very, very long time. I think these guys are much more qualified in addressing that, though.
Well, it also becomes very difficult to forecast what humans are going to do in a few hundred years. The land use change, and we could kill each other, all of ourselves off in a great war, which would probably alleviate the problem to a large extent. So
the radiation.
Yeah, right. So I think as forecasting climate is difficult enough, but as you go further forward in time, it becomes even more challenging, especially with the wild card of the human race.
How far have they gone forward? Is 100 years pretty much the limit?
There are simulations. There are simulations that go beyond that, but just to amplify on what Ian is saying, if you look at what are the sources of uncertainty in climate projections? It's basically, broadly, you can decompose the uncertainty into, uncertainty in emissions of greenhouse gas, and that's the main driver of climate change. Uncertainty in emissions of greenhouse gases, and that's really unknowable, right? Because it depends on whether you buy an SUV or a Prius. It depends on whether the state of California meets its targets for emissions. It depends on the rate of population growth in China and so on. It's literally unknowable. And the other source of uncertainty, of course, is what I would characterize as scientific uncertainty, which means we really don't understand perfectly how the system does. Even if we knew the rate of increase of greenhouse gases, we don't understand perfectly how the system responds to that. And as you look forward in time, the uncertainties in emissions become more and more important in terms of they become a bigger part of the total. So in other words, if we were projecting forward 10 or 20 years, all the emission scenarios are pretty similar, and the main source of uncertainty is scientific uncertainty. But as you go farther and farther into the future, the uncertainty in emissions, which is unknowable, really starts to dominate. And so that's I think the main reason for not going beyond 2100 is it really does become just more and more of a guessing game, I would say.
But there's one other obvious reason is that people don't care.
Well, that's right. We're all
Beyond 10 years. When I talk to the public, it's what's going to happen next year or a few years from now. To some extent, that's also dictated to this time frame. It's sort of a human length time frame, but not too far.
Yeah, no, that's right. I mean, we don't care, to the extent we care about what happens after we die, it's because our kids will be alive and maybe we have grandkids, but
yeah, that's about the length.
Yeah, after that, it gets kind of hard to care.
Question. Could you folks comment on those who think that we can manage or sort of build ourselves out of this instead of trying to control it? I think there's one of your colleagues appears to think that way, and there's of course many others. I'm wondering what your comments are on that, and whether raising levees, more dams, etc. It's a solution as opposed to control. Which I don't agree with that, but there's some that think that way.
Okay. So here's a political statement. We have California is now turning into certainly a national leader in the mitigation side of this equation. We have done very, very little on the adaptation side. All our climate scientists are telling us that change is coming. In fact, it's happening right now. There's good evidence that it's happening now. We're much less focused on the adaptation than we are on mitigation right now, and that's all the way to the top. Until just this last year, I noticed this last year adaptation started coming out of higher levels, and even in this building, the phrases adaptation started to show up. So there's the big change. We're going to shift to have to doing both, but right now most of the political focus is on the mitigation side of all this, and then adaptation. That's a long and wonderful discussion.
I think the answer, if you, I was dimly remembering a paper I read somewhere where somebody simulated, what if we just burn all the fossil fuel? I mean, that's even saying what all the fossil fuel means is not very well defined, because, as you know, if you dig deeper and harder, you can always pull up more, I think. But, if you adopt some reasonable definition of the, easily accessible fossil fuel, if you simply burn it all, how high does atmospheric CO2 get? Does anybody remember that number? It's very, very high, and I think it's really not anything like planet Earth anymore at that point. So I don't think just burning all the fossil fuel and raising the levies is a viable alternative. The other thing that gets discussed is, well, what if we burn all the fossil fuel but bury the carbon? Or what if we burn all the fossil fuel but put reflectors in space to block some of the sunlight? And in principle, you can approximately cancel the warming due to greenhouse gases if you block some of the sunlight. I mean, there's other problems with those sorts of. I mean, that the term geoengineering is sometimes used to describe what it is. I mean, I think there's other problems with those, but people are looking at that and talking about it. As for burying the carbon, Jeff, you probably know more about that than I do, but.
I'm a geologist after all.
Right.
All that carbon's my fault.
You can bury it in, I'll let Jeff talk to it, but one thing, you can bury it underground, and you can also bury it in the ocean. And, actually, in some sense, burying it in the ocean is almost appealing because, as I was saying in response to the first question, if you emit carbon into the atmosphere over time, a long time, a large majority of it ends up in the ocean anyway. And so you can think, well, okay, look, what we're going to do is just, give nature a little help here, and instead of letting natural processes remove it from the atmosphere, we'll just stuff it into the ocean ourselves and bypass the little climate change part. And that almost makes sense, except the problem is when nature pulls carbon, well, first of all, when nature pulls carbon out of the atmosphere into the ocean, it does cause problems in the ocean. It causes acidification and so on. And if we do it, it's much worse because we concentrate it. I mean, if nature pulls carbon out of the atmosphere, it's pretty dilute. If we inject it in point sources, then it gets very concentrated, and the environmental impacts get worse.
You want to, when you are driving your car here, you're taking advantage of what has occurred numerous times in Earth history, which are these oceanic anoxic events, where you have widespread anoxia in the ocean, which allows the accumulation and burial of carbon. See, that's the key. You can stick carbon in the ocean, but if there's a lot of oxygen around, it just go back into the atmosphere. So when, like I say, when you drive your car, you've taken advantage of what some geoengineers would like to do, is to create these anoxic events. If you jump in the water off Santa Barbara and you go down to a depth of 1,000 or so feet, oxygen disappears in the water because the organic material is basically consuming all of that oxygen. That's how you bury carbon. So you have to get it away from the oxygen. If you try to manufacture that, to geoengineer such a thing, I have the highest certainty you will screw it up. The results will be unpleasant because forcing anoxic conditions will probably be pretty tough. But that's what you need to basically bury carbon. You've got to go to anoxic conditions.
There was an article in Scientific American a while back. I guess I tend to look at this stuff and see, oh my God, here's another. It was basically where it was about, it's over the eons, there have been several times where there's been mass extinctions on Earth. And they used to think that an asteroid, caused all of these, like it did for the dinosaurs, but he was talking about how it turned out that they don't really think that that's the case, and that what it was a chain of events. When the oceans became acidified, hydrogen sulfide bacteria grew all over the ocean, and hydrogen sulfide killed almost every living thing on Earth.
This would be the great dying you're referring to, which is at the end of the Permian. That's one hypothesis. I want you to understand that's a hypothesis. Remember, what a big deal it was when we figured out the asteroids punch the lights out of the dinosaurs, and even that is still controversial with some geologists. But you're referring principally to the Great Dying in that case, which is when 95% of the life in the ocean went extinct, which is a pretty damn big extinction event, no matter how you shape it. This actually comes to, this is something I want to toss out to these guys, so because I get to play the role of geologist here with the big long time frame. We know in climate, when we look at historical records of climates, that there are embedded thresholds in this system, and that we cross thresholds and we get radical changes, very quick changes in climate. The Greenland ice cores suggest that such a thing occurred in the Eemian 120,000 years ago, where we'd go through periods of warming and then we'd crash into really cold, and we go through warming and crash. And of course, what people talk about is the Atlantic conveyor belt, which basically moves cold and warm water around, and when you shut off that conveyor belt, you get crashes and things get cold. So I asked to my climate scientist modeling friends here, how well do our climate models handle these embedded thresholds? Are they able to even recognize these kinds of thresholds? We know the rock record tells us that they're there.
By the way, buddy, I'm not a modeler.
Oh, okay, good. I sure as hell am not. But you are. Well, you got to remember, my colleague Jay Lund says all models are wrong, and some are more useful than others.
Okay, so you mentioned, well, threshold event speed. You mentioned this phenomenon of the ocean conveyor belt slowing down or stopping, which can happen very quickly, and it's, I think, pretty clear that it has happened many times in prehistoric past. So do models represent that? Well, yes, but the answer is yes, but. In other words, if you take, well, you can see it in models if you simply let the greenhouse gas concentrations get high enough. It does occur. You can also induce a shut-off of the thermohaline circulation by artificially in a model throwing fresh water on the surface in the relevant areas, which is the North Atlantic. So the answer is, yeah, qualitatively the models, or even semi-quantitatively, the models represent the phenomenology. But you know, they can't answer the question we'd really like to know the answer to. And the question we'd really like to know the answer to is, what does it take to make that happen? And are we there yet? Or how close are we? I guess we're pretty sure we're not there yet, but how close are we to some condition where that becomes inevitable? And that I don't think anybody has any confidence. In other words, if the model will represent the phenomenon, but it, you know, is the amount of pushing on the system you have to do in the model to make that happen, is that close to realistic? Don't know. The other threshold event I would mention is ice sheet.
Yeah,
you know,
and clathrates. Don't forget clathrates.
What's that?
Too. Well, how about clathrates too?
You can talk about that.
Okay, yeah.
Ice, you know, massive and irreversible melting of say Greenland is another sort of threshold phenomenon, which has gotten a lot of attention recently, and rightly so. And that's another one where, how close are we to that becoming inevitable? I don't think anybody knows.
Despite what Jim Hansen says, yeah. Oh yeah, so clathrates is the other one. That's these, and we're on the web, but geologists all call them earth farts. But basically this is methane, which is tied up essentially in an ice molecule, which is right below the surface, and that we've got plenty of evidence in the rock record that these things go off every now and then. The Eocene, the Eocene was one of the big ones that's been measured, where there was essentially a tremendous outgassing around the world of these clathrates, these methane hydrates, and that pumps a hell of a lot of methane into the atmosphere, and as we all know, that's a much more effective greenhouse gas. So that's another threshold event phenomena that is very difficult for us to get a handle on. Yes.
Comment and then a question. A comment on thresholds. The first one is, in the last 500 million years, there's been about 400 times that the Antarctic ice sheet has completely or almost completely disappeared, with a corresponding multi-tens of meters change in sea level. As far as the threshold, in the same period, the highest CO2 concentration is something like 3,500 parts per million, as compared to the current 385. Okay. Now comes my question. ice core CO2 data remained low during the 6 past warm interglacials, when the temperatures were 5 degrees C higher than today, according to Jarowski. That's over the last 650,000 years. His comment is either CO2 has no effect on temperature or ice core reconstructions of ancient atmospheric species concentrations are false or both of the above. Therefore, based on that, my question is, what is the relationship between CO2 and H2O on the one hand and temperature on the other? I mean, by the way, when we saw the 3,500 parts per million of CO2 concentration, I think it was like 1.5 degree temperature rise. So yes, there are thresholds. The whole Antarctic ice sheet has disappeared 400 times, and yet we see CO2 concentrations of an order of magnitude compared to today with no significant temperature change.
I wonder where you got 400 times, because that can't possibly be true.
Pardon?
Who told you 400 times? That would be almost once every million years. So that's no. It didn't work that way, and that I'm pretty confident about. So I don't know where that figure comes from. And you're wrong there too. If we lose the entire Antarctic ice sheet and the Greenland ice sheet, it's 70 meters. So that's a lot of water. So you can get a substantial rise in sea level.
The time scale on the loss is something like 50,000 years, with a much faster growth of the order of 10 to 20,000 years growth. We cover.
Okay, well, I tell you what, later you and I can debate that. Okay. Right. That qualifies in my book as a factoid. It's a near fact, but you guys answer the CO2 part. I don't get the question. So.
Well, whenever I hear these arguments about deep geologic time and there's been higher concentrations of CO2, it just doesn't. It was a different biosphere at that time, and lots of evolution has occurred since then. And so I don't think we want to be living in an analogous climate state, because we just don't know how the biology is going to respond to it in today's state. So just because it's happened before doesn't necessarily mean that it's natural and we want to force it in over the course of 100 years, personally. So that's my main reservation with these arguments.
Well, and I guess to be very frank, I'm share Jeff's skepticism with some of the facts you're citing, but I don't know enough to say for sure they're wrong. But look, in terms of the relationship between CO2 and temperature, we do know from the shorter term geological record, during the glacial interglacial cycles, CO2 goes up and down between about 180 parts per million and 280 parts per million, and the temperature varies correspondingly, and it varies by an amount, which is, I mean, again, Ian's right. That's not a perfect analogy for today, because in the ice ages, there's a lot of ice on the surface of the Earth, and it's very reflective and so on. So there's different, there's not vegetation. The comparison is imperfect, but I would say, the variations in temperature that appear to have occurred when CO2 goes from 180 to 280, as we go from an ice age to an interglacial, are approximately in line with what we expect, and the same models that we use to predict future climate can reproduce at least approximately those sorts of temperature changes. So I would say on the timescale of glacials and interglacials, the observed relationship between CO2 and temperature is consistent with what I'll call the global warming theory.
The CO2 seems to lag temperature, not the other way around the year.
Is that known, Jeff?
Well, I mean, again, depending on where you are on the rock record. I mean, when you're looking back in the rock record, we're just in the late Mesozoic. No, they're about insane. But of course, our resolution fades when we get back that far. But this is actually a standard debate that we hear, and I've got just as many colleagues in my own department who will tell you, no, they're right in sync, that they're right tied in together, and that
in the recent record, though?
In the recent record, yeah, and actually as far back. I mean, like Isabel Montanez, it works all the way back to the Permian, so you can track it cleanly.
How do they measure CO2 when you get out, when you can't,
you have to use
go back so
geochemical proxies. You have to use geochemical proxies to do it.
Carbon 12 ratio in carbonates and marine microorganisms, they're fossils.
Okay.
Right.
But ice cores go back.
Yeah, I'm
yeah, now
that's
400,000. We can go at least 400,000 ice cores. How about somebody else with a question?
Back there.
I just have a question. There's a debate going on whether this is global warming or global cooling right now, and I'm really curious about how does one measure the temperature, especially when you're talking about 100 years ago versus now, and when the measurement tools available were a lot more primitive than they are now. And the other question along with that is, how do you know that a temperature difference is not merely, microcosm of that area versus a global, global change? I know there's a lot of controversy right now on that, so I wanted to know if you could clarify how the finite, minute amount of change that we're talking about has been established. Margin of error within even equipment that we have today.
The temperature record in the last 100 years has largely been a pretty standardized thing. It's a standard mercury thermometer, which has not changed and which we still use today, partly, even though it's very archaic, partly in order to keep a reference for these older records. The precision, at any individual site, the temperature changes are a number of degrees in any given year, any given time period. And the precision of the instruments is quite good there. The bigger issue has always been, you have measurements, especially 100 or 200 years ago, or a longer time, at fairly small number of places around the world, and how representative is that? And there's been an extreme debate about that, and people have tried to carefully analyze that, and then merge it in with the ice core and other kinds of geological or paleological records which are available, and they agree quite well. That doesn't say that there aren't some imperfections, but those you expect to be relatively random, and there's some noise, and that's always been accounted for in all of the IPCC reports, and that's been estimated. So that is not a major issue.
If I can add to that, though, the thermometer record goes back sort of 150 years, and as Brian mentioned, as you go farther and farther back in time, the coverage gets worse and worse in the sense that the fraction of the Earth where there is good measurements gets worse and worse. And the issue with the thermometer record is very few. Most of those measurements were made for purposes other than monitoring long-term climate change. They maybe have been made for short-term numerical weather prediction purposes or some other reason, agriculture, whatever. And so there are issues where the local environment can change due to, say, urbanization, or somebody chops down a tree nearby, or they decide, okay, instead of making the measurement at 2 o'clock, we'll make it at 12 o'clock because I feel like having a nap at 2 o'clock, or all sorts of things. And I think Brian's point is true, though. Well, partly we try to avoid deceiving ourselves by carefully looking at the records and correcting for those things. And it's also true that they shouldn't systematically bias. Those errors should average to zero if you have enough measurement. The other point, though, is that the thermometer record is only one thing. There are geological reconstructions of temperature which we can use during the thermometer era. There are recently satellite reconstructions of temperature which have their own set of problems but are consistent with the thermometer record. And the other thing is there's other evidence that there's warming. I mean, glaciers, by and large, almost all of them have become smaller over the last decades. We see things in the Sierra, the snow is melting back. There's other sorts of observations are indirect indicators that there is warming. So there's no question. I think there's no question that there's warming, or there has been warming certainly over the last 50 years, 100 years.
Yeah. In terms of solutions, it seems to me that most people think that we need to reduce carbon emissions or limit them to what they are today over the next 50 years or so to stabilize carbon in the atmosphere. Yet if you look at the trends, it's impossible because we're doing just the opposite. We're just going out of in the stratosphere. Having said that, Robert Sokolow, a Princeton energy specialist, has written up a plan called the 7 Wedge Plan. It was written up in National Geographic magazine, and I've read about it a lot. Are you familiar with that plan, or could you comment on is something like that really feasible, that this can be done, that we can really reduce carbon emissions over the next 50 years or so to the extent that he suggests?
Just look at me again. I'm gonna actually give someone else the opportunity to answer the question, but I want to just note something you said in your question. You said, well, something about we can stabilize emissions and therefore stabilize CO2, but it actually doesn't work that way. If you stabilize emissions, atmospheric CO2 keeps going up. Okay, in order to stabilize atmospheric CO2, you have to stop emissions, not
stopping them at today's level.
no, you have to stop them at 0. Well, no, look, to first approximation on the time scale of 100 years, CO2 accumulates in the atmosphere. Okay, so if you want CO2 concentration to remain flat, you have to emit 0. Okay, not the same as we're emitting today, but 0. That's a little scary. And then over time, the oceans and so on will absorb, and the CO2 very gradually will go back to them. So that can be discouraging, but that's the way it is.
And that was done by the IPCC, and the temperature still rises a little bit in the next 100 years.
Right. Okay. But wait, we didn't answer his question.
What was the plan?
The 7 Wedge Plan and what he's done is taken that projected increase in carbon emissions over the next 30 or 40 years, and he's divided that into 7 parts. He calls wedges, and the article seems very plausible. I mean, this is something that really can be done, but that's why I'm asking the question.
Well, I guess on that, I'm no more of an expert than anybody else. I mean, I read the article. I mean, I think it came out in Science about in 2004 or something. I read it and had the same reaction you did, which it sounds reasonable. But I guess what I sort of took away from it is, okay, one way to address this problem, unless some miracle occurs and somebody discovers some silver bullet, one way to address this problem is sort of a little bit of everything. It's kind of how I interpreted it. I thought there were more than 7 wedges, or maybe they got reduced to 7. But anyway, each wedge is, I forget what they all are, but it's like it's sort of through a combination of things, conservation, so on, we can solve the problem. So that was sort of what I took away from it. Well, maybe through a little bit of everything, that's enough. But I'm no more of an expert on that than anybody else particularly.
You sure would hate to be teaching younger people that there's no hope, right? Yeah.
The question is there a viable plan around?
Oh,
Bill McKay's 100 nuclear reactors.
Are there individuals or organizations in China or India that have a lot of potential to make impact in their societies as far as addressing climate change that come to mind? Can you think of anybody? Do you know of anybody?
That I'm aware of.
Yeah, it's quite discouraging, having just got back from China. The development there is tremendous, and the reliance on U.S.-style automobiles is growing at leaps and bounds. So
And every 50 days, they're starting a new coal-fired power plant.
And obviously, I think recent history shows that environmental and safety is not one of their top concerns.
One of the topics originally proposed for this session, I think, was long-term climate change mitigation strategies.
We couldn't find anybody willing to talk.
Was that today's topic? So I'll just hazard with this auspicious panel. Right. There you go. If you might each address some element, I know this is kind of blindsiding you because it's a big topic to deserves thinking about ahead of time. Some elements of this long-term, and in parentheses it said 2050, maybe 2100 climate change mitigation strategies for California? What would one or two elements of such a strategy be? And I think of a colleague at Virginia Tech, Chris Nelson, who's an urban planner, who came out with an interesting tableau for between now and the year 2050, that all of the constructed buildings, the built environment that will exist in 2050, more than 30% of it will be built between now and then. So there is an opportunity from the planning standpoint to reduce the carbon footprint in those structures that will be built. That would be, to me, a long-term mitigation strategy between now and the end of this century. So I wonder, again, given the caliber of the panel, if there could be some estimate of what your elements of the mitigation strategy would be.
Well, some of the 22 caliber. Yeah. It's three things: transportation, transportation, and transportation. I mean, when I talk to my colleagues at UC Davis, that they say this is going to be the toughest nut to crack in terms of dealing with that is the transportation. Not just the fact that you're using internal combustion engines, but that we have built an entire society about long distance travel. I mean, the people in this room, a handful of you did not travel by car some substantial distance to get to your work, and really have no except Bill. But you came on a jet. No. But if you came on a jet, you really had a big carbon footprint. So I think that's going to be in fact, I think the governor's plan for mitigation, when we do get down to the nuts and bolts of how to achieve those goals, transportation is our biggest, toughest thing to deal with.
So the strategy then would be
focus on transportation.
Yeah. Kind of transportation.
Shorter transport distances, constant, communities that are close to work. I mean, instead of the traditional model that I grew up with in Southern California, that is extended throughout all of California, is maximum length of commute somehow equals a higher quality of life. I never quite figured that out.
I suspect there's people in the audience who know more about, could better answer the question than I can.
You're in the panel.
Well, yeah, but you guys, there's a lot of expertise on the other side of the table.
I comment.
True.
Each person in the United States has like 150 to 200 energy slaves. In other words, something like 100 horsepower. The energy goes not just for transportation, it goes for hauling food, for manufacturing, for agriculture, for fertilizers, et cetera, So we consume a lot of energy. Obviously, you want to be more efficient, use less energy. But the other side of the equation is, for a relatively high standard of living, you have to produce the energy. For transportation, you could contemplate ammonia as a fuel or hydrogen as a fuel. In the case of both of these, your waste products are water vapor, and in the case of ammonia, you have the additional nitrogen. That's it. But that takes a lot of energy. So that in turn impinges on your energy generation infrastructure. Where are you going to make all the energy or produce all the energy in a non-greenhouse harming way, climate change harming way, to produce these transportation fuels and produce all this energy? One obvious solution is nuclear. Now, I know that a lot of people are very much concerned about nuclear. So that's going to be a major debate in this country for the next few decades.
I heard a cool idea yesterday, which is not the solution to all the world's problems, but I thought it was a cool idea. It was a discussion of wind power, and wind power is great in the sense that there potentially is a lot of energy that can be tapped. But the problem with it is the wind blows when it wants to, and in many cases it blows at night when we have essentially too much electricity. And so it's an uncontrollable resource, unlike a fossil plant or a nuclear plant or even a hydropower where you can open it. So I think I don't think it's actually even been prototyped, but the idea is you can have big wind turbines, and when you can't, when the electricity is not needed on the grid, you could actually use the wind energy to manufacture hydrogen right there. And then use the hydrogen as a fuel for transportation or something. So in that sense, you're using hydrogen essentially as a way of storing. No,
in all et cetera, is much more efficient in terms of the amount of the standard of living, GDP per fossil fuel unit. So there are a number of possibilities still that exist in the current. Looking into the future, this mix of things that was discussed before, the 7 deadly sins or whatever it was, all of those are probably possible.
If I can make, without giving you a specific answer, I mean, the way I would approach the problem of the universe, I would say, through a combination of government funding and market, and the way I think it should work ideally is, the government can fund engineers and so on to develop new ideas like making hydrogen from wind power, and then have those ideas and then let the market decide which of those it likes and which of those work. The market isn't as great at developing the technology. The market is great at developing the technology. Put it out there and see what sticks. Kind of thing. That's just sort of a philosophical approach. It's not like it's interesting ideas. Like, some of them are going to work, some of them won't work, some of them will work. Let them put them out there. Let's see what that's what about.
Matter of getting everyone involved in that cause, and I think we're on our way there. Actually, if you had a project, the talk in the press is about a project on the scale of the Manhattan Project, where we were all kind of put together for this common cause and just doing as much creative problem solving as possible. But I really think you also have to realize that you need to start looking at longer timescales than we've ever really been forced to deal with. And another issue I would say would be don't have as many kids.
Oh. Well, actually, you made me think of something which I think just to reiterate what you said, I do think one way to say, I think climate change is not a problem that they can solve. So many times when there's a problem, we think, oh, they should do this, they should do that, they, and we always want the problem to magically disappear. We want people in City Hall or Washington or whatever to solve it. And by the way, don't raise our taxes because we don't want to pay anymore. We're already paying too much. I think climate change ain't going to be like that. I don't think it's a problem they can solve. I think it's a problem we all have to work together to solve.
I'd like to ask a question about the CO2 history for the last 200 years. In other words, the standard scenario is the CO2 and those cranks up as industry melt and fossil fuel consumption going current 385. So I mean, two short comments on this question. The first comment, the atmosphere, I have a classic fingerprint or signature of fossil fuel burning. So I think it's spot on to say, at least I've bought the statement that the CO2 increase we see in the atmosphere currently is due to fossil fuel burning. I think it's pretty much of a given. But on the other hand, my other comment is, according to Destiger in 1985, the isotopic dating of air species in ice cores, when you look at their ages of the gases, the various gases in the atmospheric air samples and the air bubbles in the ice cores, and you look at also the isotopic dating of the surrounding ice in the ice cores, you find that the gas ages are several tens to several tens of thousands of years younger. That's in the air bubble. Well, anyway, my last point is, in the time frame 1712, there was a significant Slocum asked the question, why did ignore all of those data points, pre-industrial and post-industrial, which show concentrations anywhere from 215 up to 570 parts per million. Now, there comes my question.
Okay, but wait.
All of this throws considerable doubt, at least in my mind, after this pre-post-industrial CO2 scenario where it starts low and then goes shooting up.
Because you think it was this high.
Oh, wait. The hockey stick picture is not a CO2 history, it's a temperature history.
Well, okay, I'm
Okay.
talking about the CO2 ice core data, and then it goes up into the Mauna Loa data.
Okay, but that's not the hockey stick.
Okay.
Okay, so this is a good place to sort of deal with that kind of thing. I'm a geologist, and I deal all the time with people who doubt evolution. One of the things that I've noticed that they'll do is they'll selectively cherry pick some contradiction somewhere in the fossil record and use it to unravel everything. But I'm trained as a scientist, and a scientist says when you have a question, a fundamental question, or a hypothesis, you don't use one thing. You use many things. You test it with a broad array. And you're going to get some things which might be contradictory. But when the overwhelming body of evidence points toward this conclusion, or at least this test of this hypothesis, you tend to get scientific consensus on this. And what I'm hearing you say, or I think I'm hearing you say, is that you don't believe that there is a relationship between CO2 and warming and greenhouse gas emissions and warming, despite the fact that a very large, august international body tackled this issue and came up with consensus. Again, when you have so many disparate lines of evidence from geochemistry of the oceans, geochemistry of the ice, the atmospheric geochemistry, our observations made around the world, I think that part of the debate's over with. We've moved on beyond that.
The relationship between temperature.
What I'm saying is, what I see on the web is that the Antarctic ice core data is a small subset of the total. And that shows like a lower bound for any given calendar year when you compare it with these other 90,000 atmospheric measurements throughout that similar time frame.
Again, okay. So what? I think is my answer. I think the answer is precisely. You nailed it. Your perception. The general perception, scientific consensus, as close as you're ever going to get in science, is that is your perception. It does not square with the current science.
So you're questioning whether the pre-industrial CO2 concentration is really 200.
When you look at the atmospheric temperature measurements, going back from 1712 to 1890, you see this sort of thing 3 or 4 times.
Temperature measurement?
CO2 concentrations. These correlate with volcanic eruptions. And what you see, as I said, the lower band is indeed the Antarctic ice core data. This is the order 215 parts per million between the volcanic eruptions. But you look at the peaks on the 90,000 data points, 3 or 4 times, there's several peaks, and they're all up in the range of 550 to 650 parts per million. So I'm not cherry picking. I'm saying there's 90,000 data points out there which the IPCC ignored. They did use, when they looked at the atmospheric measurements, they did use the data which was the lower bound of this field, where you see these oscillations going from 1712 to 1890. And those do correlate with the Antarctic ice data, the ice core data. But they ignored all the data above there off that lower bound. And I don't understand
Well,
that.
look, I can't answer that question. I just
Okay.
comment. I mean, you've said enough things that are wrong that I'm skeptical of your facts. I'm not an expert. I'm not an expert on that either.
And if people are being exposed
Don't
to
believe
all
everything you see on the web. Is this news? Newsflash. Don't believe everything you see on the web.
The physical relationship between temperature and CO2 is physics that was established around the time of the Spanish American. I mean, it's just
That's my area of expertise.
okay. So it's just I don't understand why people still argue about that.
Because they argue because there are contentions that it's the water vapor trapping that's anywhere. You see various estimates from 95 down to 60% of the total, and the CO2 being the difference. The CO2 being 5 to 40%, depending on whose estimate. That's why they're questioning whether CO2 is really driving global warming, because they contend, these authors, that, hey, it's the water vapor variation due to sea surface temperature that's the real driver, not necessarily the CO2. The CO2 is insignificant in that scenario.
It doesn't matter. It doesn't matter if it's the sea surface or if it's the land surface. It's all going to be mixed around by the climate system.
And water vapor water vapor as the climate warms, as CO2 go up, there is this so-called water vapor feedback, where as the atmosphere warms, the moisture carrying capacity gets greater, and that has happened. Right. And part of the warming, I mean, if you want to break it down, if you look at the warming over the last 50 years, part of it is in fact due to water vapor. But that increase in water vapor is an inevitable consequence of increase in CO2. You can't.
Well, the argument is whether the driver is CO2 or solar radiation or some other mechanism like the cloud formation effect that's varying the solar flux, which varies the surface temperature, which varies the water vapor in the atmosphere. In other words, is that the driver? I mean, that's kind of where the arguments are. And a lot of people believe that the issue that CO2 is a slam dunk is not a done deal.
But if you have to go through those kinds of convolutions to argue we shouldn't do anything in response. Well, I mean, if you're trying to drill holes in the science,
not the driver. In other words, if it's indeed
mitigation for now,
then CO2 mitigation, well, it's a waste of time. Then we ought to allocate our resources elsewhere.
You know what?
But from a cautionary step,
I want to get the last word.
It's 1 o'clock. I think.
Okay.
We had one. We're going to ask a question. She's been very patient. Let's have her as the last question, and we'll go from there.
Okay.
There's something about transportation being a key issue here. And I was wondering if there's, coming from a completely non-scientific background over here, is there a difference between air transportation that's increasing, that is emitting right into that level, and ground transportation that's down here and I don't know.
Well, actually, I can't. I want to tell you, it was a plane flight with my son, and I think about my son when we talk about this, because in 50 years he'll be looking at retirement, and that's a good time frame for me. And so 2050 is a good number for me to think about. And we were riding in a jet back from Florida, and he said, "Dad, I know about hybrids and I hear about hydrogen power. If they got anything in mind for making plane travel work other than fossil fuels?" They don't. So there's where your big impact is going to be. It's going to be very difficult to adapt there.
the CO2.
Yeah, the CO2.
Is there anything we can do to get rid of plane travel or reduce plane travel?
The fact is, plane travel is inefficient in terms of fossil fuel.
I mean, I think newer jets are more efficient than older ones, actually.
But still, the carbon footprint when you fly is
It
Is
is.
there anything like on the road, or not like literally on the road, but in the works on like the intercity high-speed rail that's coming up in the U.S. Maybe.
Wait, okay.
I can answer. I don't want to ask a question. I don't want to ask a question. I want to answer a question. Okay.
Thanks, everybody.
Is it not just the CO2 involved?